Hello, class. Okay, so we're going to talk about an infinite plane, which of course does not exist. But let's say we have an infinite plane with a charge density sigma, and we want to know the electric field at a point, well, just some point. And we're going to do this in two ways. One, using Coulomb's law, because it'll be good practice, setting up this like this integral and integrating over the entire plane. And also we're going to do it with Gauss's law. And so another reason we're going to use Coulomb's law to do this is to just show the contrast. So there are a few cases where Gauss's law can be used to calculate electric fields. And when it can be done, that's the way to go, because it is so much easier than using Coulomb's law. Many cases it is. So let's start out by using Coulomb's law. So actually, I left this here because we're going to use Gauss's law, but might need the space. So we want to calculate the electric field at this point P using Coulomb's law. So again, this is a perspective where the plane is coming out of the board. I want to also look at it looking down from point P. So I'm drawing it as a finite plane. And let's say this is point P, which is out of the board. I'm just centering it there. And so what we're going to do is let's look at a ring of charge. A very thin ring that is a radius r and a thickness di. And so what we can do is we can look at this infinite plane as just a sequence of rings of different radii. So we could build up a whole plane. We'll have a very small ring here and then another one around it, and they're going to perfectly cover the plane. So we're going to find the electric field due to that ring, and then we're going to integrate from r equals 0 to infinity. And this is why having an infinite plane, it's relatively easy to calculate the electric field versus a finite plane that would be a lot more difficult. Or at least if we had like a rectangular or a square plane. If we had like a finite disk, that would be manageable. But like a rectangle, that would be pretty complicated. So yeah, let's just look at this ring here. So let's say we're looking at a point, a distance d, above the plane. And so our element of charge is basically over here and here. It's a circle that goes all the way around. So this distance, I'm going to call this capital R, actually. Because in our formula, we're used to using E is KQ over R squared with a lowercase r. And I want to stick with that. So let's say that this distance here is capital R. So we're considering a ring with a radius of capital R. And that would make this, the R in the formula is a distance from the charge to our point. And so that would be lowercase r. So we can see that r squared equals big R squared plus d squared. Okay, so the first thing we want to do is find out how much charge is in this ring. And so it's a ring, so you can picture kind of, if you have just flatten it out, and we have a rectangle. So the charge, dq, is going to be sigma times dA. So sigma is the charge density. That'd be like how many coulombs per square meter. And the area of this ring is going to be 2 pi r I'm going to make this a capital R as well, dr. So basically the circumference is 2 pi r, and the thickness is dr. Now again, that formula would not apply if dr was, really anything finite. But if dr is very small, then this becomes a good approximation to the area. And in the limit that dr goes to 0, it becomes exact. So dq, I'm going to write this, let's put 2 pi sigma times r dr. Okay, so that's great. We can plug that in. So let's do this. We have E. Let's look at the magnitude of E. That is Ke dq over r squared. And then we can plug in, actually in this case, I think it would be more convenient. Let's do that. Instead of Ke, let's use 1 over 4 pi epsilon naught, because then dq is 2 pi sigma r dr, and then we divide by r squared, and we can get some cancellation here. So the magnitude of our electric field, the 2 pi and the 4 pi, well, that just reduces to 2 in the denominator. So we have sigma r dr over 2r squared. And that little r, that's big R squared, that little r squared is big R squared plus d squared. Okay. Sorry, this is dE, the magnitude of the electric field due to this charged element here. And the reason we picked a kind of a ring of charge is because like every point on the ring is the same distance. However, we do have, this is just the magnitude of the electric field. What about the direction? So if we look at this point here, we have an electric field that points this way, just radially away from that charge here. If we look at this point, we have a dE, pointing in a different direction. However, because the magnitude is exactly the same, and we're dealing with a circle that's centered on this point directly below P, like these angles are going to be the exact same. So if we add up these two vectors, the horizontal components are going to cancel out. So really what we want is dE. Okay, I just drew that P there, and then I had to erase it. Let's define this angle to be theta. That would make this angle theta as well. And so the component that we want is dE cosine theta. That is the vertical component of the electric field. And again, we could consider the horizontal component as well and integrate that, but when we go around the whole integral, that's going to end up being 0. So again, we have a piece here that points this way, a piece here that points that way. Those two components cancel each other out. And so we can just worry about the vertical component. And again, that would apply all the way around the circle. So this is just like a cross section where we have 2 points. But again, that would be like, say, here and here. Those components are going to cancel out. If you look at that point and that point, same thing. But they're all going to have that same vertical component. And we can see from this picture that cosine of theta is d over little r. So we have sigma times d dr. Let me just move this up a little bit. And then on the bottom we have this 2. And then this is r squared. Now we have r cubed. So cosine of theta, that'd be d, which we put here. And now we have r cubed. So we'd have r squared plus, yeah, let's do this. So r is r squared plus d squared to the 1/2. And so now we have r cubed, so this would be to the 3/2 power. So that's the only part of the electric field we care about. That's the vertical component. And so now what we want to do is integrate from r equals 0 to infinity, and that will cover the entire plane. So the electric field at point P, we can take a little bit out here. We can take out the sigma over 2 and this d. So sigma d over 2. Yeah, I should avoid using d because this looks like dr. So here, let's, yeah. Sorry if that was confusing. Should have called it something other than a lowercase d. But anyways, we can take that out. And then we have the, oh wait, yeah, we want to keep the other r there. And now we have the integral of r dr divided by r squared plus d squared to the 3/2, where r goes from 0 to infinity. And this looks like another u substitution. So let's say u is equal to r squared plus d squared, then du is 2r dr, and the lower limit, if r equals 0, so if r is 0, then u is d squared, and if r equals infinity, then u is also equal to infinity. So let's make this change of variables. We have sigma d over 2. Now r dr is 1/2 du. And then we have here, this is u to the 3/2. And we're integrating from d squared to infinity. Let's take this 2 out. And so we have u to the minus 3/2 du from 0 to infinity, or so again, the integral of u to the minus 3/2, that's u to the minus 1/2, which is 1 over the square root. Sorry, 1 over the square root of u. So we have u to the minus 1/2 divided by minus 1/2. So we'll put a minus, again, it's divided by minus 1/2. So we can put a minus 2 there. And we're integrating from d squared to infinity. So let's plug in our limits. We have sigma d over 4. And here we have, we plug in infinity. So we have minus 2 over the square root of infinity, which is 0. And then minus this negative 2, so we have plus 2 over the square root of d squared, which is t. So what we're getting is the electric field is just sigma over 2. And now I'm concerned because the units aren't working out, and that's because I forgot this epsilon naught everywhere. So that's a bit of a problem. So It's always good to make a mistake in the first line, and then you have to carry it out everywhere. So yeah, there should be an epsilon. I'll just fill them all in. Okay, it's not that bad actually. So yeah, I forgot that epsilon naught right in the beginning, so we're getting sigma over 2 epsilon naught for the electric field at this point P. And something that's pretty remarkable is that it doesn't depend on D at all, the distance from the plane. And you might think the farther away you get, the weaker the electric field is going to get. However, it's an infinite plane. We shouldn't necessarily expect an intuitive result here. The farther away we go, if you picture an infinite plane, if you move farther away, you're still not going to see a boundary. It's still going to be infinite. So that's what we're getting using Coulomb's law. Sigma over 2 epsilon naught. So what I want to do now is do the same problem, an infinite plane, but I want to use Gauss's law. And let's see if we get the same result. So let's see. Let's erase all of this. And let's draw our infinite plane. And one thing we have to state from symmetry is that the electric field has to be perpendicular to the plane. And again, that is true. It has to be true because of symmetry. Like it can't say point to the right. The idea of symmetry is if you do something to it and it looks the same. Like say that we have an infinite plane and we rotate it. It still looks exactly the same. However, let's say that we had our plane like this. And let's say the electric field was let's say it pointed in this direction. Let's do something like this. Now, what if you look at the plane and you look at the electric field that looks like that? Say you turn away and somebody rotates this plane 180 degrees. Well, the electric field would rotate with it. And now you look back and the plane is exactly the same, but now the electric fields are pointing in the other direction. And that doesn't really make any sense because there's nothing you can see about the plane that is different. And so the electric field is a property of this plane. It's generated by the plane. So if the plane doesn't change, then the electric field can't either. So the only electric field that can exist would have to be perpendicular. And again, that's a nice thing about infinite planes. Just real briefly, why do I keep talking about these things even though they don't exist? A very important thing we're going to cover later is something called a parallel plate capacitor, where you have two planes that are, of course, finite, and there's an electric field between them. And the thing is, as long as you're not close to the edges, the electric field in between these two planes is going to look just like this. They're going to be just perpendicular from one plane to the other. Like one of these planes is going to have a positive charge, the other is going to have a negative charge. And the electric field is going to look just like this until you get to the edges where they kind of start curving outwards like this. But if you're just looking inside, the edges only, like if the planes are close together in particular, these edge effects are kind of insignificant. And so the infinite plane is a very good approximation of the electric field inside a capacitor. And that alone is enough reason to study an infinite plane. because it gives us a very realistic result for a very important problem. So just if you're not happy with dealing with something so ridiculous, well, now we have hopefully a good motivation for that. So we're going to use Gauss's law now, and I'm going to draw a surface around it. Again, we can draw any surface that we want as long as we don't do something ridiculous like a Klein bottle, or a surface that doesn't even have a normal vector because of the way it's defined. And what I'm going to do is I'm going to pick a cylinder. Here, I've got a cylinder right here. So, say this is, I wish I could cut it with a plane, but I can't. So, say there's, like here's a plane, cylinder above it, and another one below here. Now, the key to Gauss's law, the flux is equal to the charge over epsilon naught. Now, the thing is, this is for, I'll just write CS, for closed surface. So we have to have a closed surface. And the charge is whatever is enclosed. So basically, here, if this is our surface, the charge would basically be how much charge is in here. So what charge is in there? That would be the Q. There's a lot of charge outside. We don't care about that, like we talked about earlier. That's not a factor in Gauss's law. And so let's find out the amount of charge. It would just be this much. So let's say our cylinder has an area A. Then our charge would just be sigma times A. So that's our charge enclosed. And now let's calculate the flux through this surface. And so again, this is a part that might be easy to screw up because we have to make sure that we calculate the flux through the entire surface. So we'll keep this here as a, oops, make this noise. So let's say this is our surface. I can only place our, this has to extend below as well. And here is our electric field. So let's break this surface up into 3 pieces. Let's say surface 1, surface 2, and surface 3 would be the going around the cylinder. And so our flux is going to have 3 parts. The flux through surface 1 plus the flux through surface 2 plus the flux through surface 3. And that's equal to sigma A over epsilon naught. That's the charge enclosed by our surface divided by epsilon naught. Okay. Now, the flux through surface 1. So again, say this is our electric field. We know it's perpendicular to the surface. Our area vector is, by definition, it's a normal vector. It's perpendicular to the surface. So for surface 1, we can say that E dot dA is E dA without the vector signs. So we don't have to worry about the direction between the electric field and the normal vector. And also the electric field everywhere along this surface is going to be the same. We actually saw from Coulomb's law that the electric field doesn't depend on the distance at all. But even if it did, the point is it's going to be the same everywhere along surface 1. And so when we integrate over the surface, we're going to get the flux through surface 1 to just be E times A. That's it. Because the electric field is constant, we can take it out of the integral. The integral of dA is just A. So let's look at surface 2. Now, here, let's say this is our surface. Here's the part of the cylinder below. And again, the electric field is like this. The normal vector, remember, it points outwards. So the area vector here, let's call that, say, A1 and A2. And again, just like before, the area 2 vector and the electric field are parallel to each other. So for surface 2, we also have that condition that E dot dA is just E times dA. And just like before, the flux through surface 2 is going to be E times A. So now let's look at surface 3. So here's our cylinder. Here's our electric field. Here's our electric field. Try that again. Sorry, the electric field is vertically upwards, and the normal vector is going to point, it's perpendicular. So it's going to look like this all around the cylinder. And you can see that they're perpendicular to each other, no matter where. Like the electric field here, these two vectors are always going to be perpendicular to each other. So for surface 3, E dot dA is 0. And so flux through surface 3 is 0. Yeah, like the electric field exists on around surface 3, but it's just moving along the surface. It's not passing through surface 3. So there's no flux through surface 3. And so if we go back to this equation, we have flux 1 plus flux 2 plus 0. So this is going to be 2EA. Is equal to sigma A over epsilon naught. And something very important happens here. A cancels out. And that is essential that that happened. Because remember what A is. That is the area of our cylinder, like the flat surface on our cylinder. And again, this is a mathematical surface that we created. And so we just created it to help us calculate the electric field. What if we picked a different cylinder with a different area? We better get the same result because the electric field doesn't care how we go about calculating it. And so we have to get the same result for any area. So the eventual electric field that we come up with can't depend on A at all. So it's essential that that canceled out. And then if we divide by 2, we get the electric field is sigma over 2 epsilon naught, which is exactly what we got from Coulomb's law. Now, Gauss's law was much easier to use. Now, I do want to just have one warning about Gauss's law. Like in these examples we used, we usually end up with this result that the flux through some surface is going to end up being the electric field times the area. Now, how often does this occur? Now, in general, the probability of this occurring is virtually 0. It almost never happens. And it has to be a very special case where the flux, where this equals this. That is certainly not true in general. And, you can draw an infinite number of surfaces. This applies to any surface. And for the overwhelming majority of cases, this is not going to be true. So, and the reason I'm kind of mentioning a warning here is because we only use Gauss's law to calculate electric fields in those special cases where this equation is true. And so when you're just learning this, it's like, you know, I'm going to give you problems, or the book is going to give you problems, where you calculate the flux, and because we know we're going to use it in a case that's going to give us a useful result, the problems that we pick are very untypical of what can happen in the real world. Like if we have a different type of geometry, like say we have a finite plane. Like say we want to calculate the flux, like say that this board here is charged, and we pick this as our Gaussian surface, you know, the flux through this surface is not going to be the electric field times the area. It's not going to be something we could easily calculate at all. So again, generally it's just, you can get this impression that the flux is always going to be the electric field times the area, because every time you use Gauss's law, that's going to be the result. However, we're only using Gauss's law in very special cases. And so don't think that whenever you see Gauss's law, the flux is just the electric field times the area. So anyways, yeah, we did kind of the same problem two ways. Clearly this was much easier, but you still have to be careful. Yourself to consider, make sure you have the flux through the entire surface if you're going to use Gauss's law. So we have to consider like the top and the bottom, and then that cylinder, the curved part of the surface going around. And yeah, as long as you're careful, and should work out okay. So I think that'll be it for this video. And you know, the last thing we have to talk about is conductors. That'll be a separate video.